Good morning to all. So in previous classes we finished our first chapter, which is entirely related to the network topology. So there we learned the different topics, cut set, tie set matrix, how we are going to write the incidence matrix, and how the coupling will work in electrical circuits as well as the magnetic circuits. Next we'll go for our unit 2 as per curriculum, so which is steady state and AC response, or that is also called as transient response of different networks. So here we are using passive elements, that is resistor, capacitor as well as inductor. So there we are going to learn the steady state and transient responses of RC, RL, RLC circuits. Okay, so but what is meant by a steady state and what is meant by a transient state, and what are the responses we are getting in this particular chapter? That is, first one is a DC response, AC response, natural response or forced response, transient and steady state response. So here, whatever the signal you take, if that is vary according to the time, so after in a time being, it is continuously varying up to the variation of according to the time. That response is called as a transient response. So whenever that continuously varying, like you take one step signal, for the step signal that is undergo a steady state response, that is second order system. So can you, if we consider the second order system, that is underdamped system response. Okay, so for the steady state input, what you are getting, that is which is a underdamped response, first that will goes to the first that will generate the oscillations. After some time being, that will stay in particular band or particular value. So up to that is not staying the particular value, that is continuously varying, that is called as a transient response. Whenever that will maintain a constant output, or that if that is reaches to the input value, then at that point the response of the output signal is called as a steady state response. Okay, so if you apply to that particular circuit, let us take that is a RC circuit. So for that RC circuit, if you apply the input signal, input that is as a DC, like V is equals to some 5, or input voltages which is not varying according to the time. So if you apply a constant voltage or constant source to that particular circuit, then what type of response that will produce is, that is called as a DC response. So whenever you apply the time varying signal, like V is equals to some 5 sin t, so that voltage is varying according to the time. So that time, if your input is varying according to the time, that type of signal you are going to apply to the circuit, then that response will be produced by that circuit is called as a AC response. AC response. Here, natural response and forced response. What is meant by natural response? Whenever you are going to apply some input, that will produce this output, no? So that actual output that will generate by that particular input is called as a natural response. But I need to get output as this particular specific value, nothing but I am going to force that circuit to get that particular output value. So at that situation, whatever the input you are going to apply, so that response is called as a forced response. That response is called as a forced response. So these are all we are going to learn in the second chapter. So in this class, I am going to explain the DC responses for the different circuits. So DC response is nothing but here you are going to apply input as a DC for different circuits. Like first I am going to explain RL circuit and what is the response of that particular circuit, how the waveform will be generated. And next one RC circuit, and next RLC circuit. For these three circuits, I am going to apply input as a DC voltage. For that one, what is the output generation and what is the output equation and response will be, that we are going to see in the second chapter. So now I am sharing the whiteboard to explain these topics. So here, in the transient response, that source will be forced, that we are going to get the particular output. So that is called as a complementary function. And steady state response, that steady state response, that we call it as a particular integral. So we have any response or any output that may represent in two ways, or like output equals to x plus y, let us take, where x is a complementary function and y is a particular integral. So this type. So here, if we use the energy element as independent variables, independent of sources, then that is called as a natural response. If we are going to use the independent sources, that response is called as a forced response. So here we have natural response as well as a forced response. Natural response and forced response. In the natural response, here sources are independent. Sources are independent. Here sources are dependent. So let us take, first I am going to just DC response and AC response. In DC response, input will be DC voltage. In AC response, input will be AC voltage, nothing but varying with time. So first I will explain this DC response for three circuits: RL circuit, RC circuit and RLC circuit. So first we will go for DC response of RL circuits. So basically RL circuit is nothing but which consists of one resistor as well as L, that is inductor. So here, from here I am going to apply source voltage. So source voltage, let us take, that is V. And here, in order to activate this circuit, here I am connecting a switch. Whenever switch is open, that circuit is in the open condition. Whenever switch closes, that will perform the operation. So this is R and L, let us take. So the current passes to this one is I. So can you apply the KVL for this loop? Yes, this will, whenever switch S is closed, if switch S is closed, that will form a loop. So what is a loop equation? Here current is entering at the negative terminal of the voltage source. So we should write that source value as positive, V minus RI, voltage across the resistor. And what is the voltage across the inductor? That is L into di by dt. The algebraic sum of the voltages in a particular loop equals to 0. So if we send that one to the RHS, Ri plus L into di by dt will get. So can we write this as a di by dt quotient? So di by dt, I am writing like this, plus Ri equals to V. So whenever di by dt plus, here L I am sending this side, R by L into I equals to V by L. So which is in the form of, like when you calculate the particular integral and complementary function, so that is in the form of what? Which is y bar, that is dy by dx plus px is equals to k. This is in the format of dy by dx plus px equals to k. So where p, so for this one, what is the solution? You already came across in the maths, that is x is equals to e power minus px integration of k into pt dt plus c into e power minus pt. So this is a response of this particular circuit or particular equation. So here if dy by dx plus px equals to k. If our equation is in this format, then we can write the equation, that output equation or output response for the x is equals to e power minus pt integration of k into e power pt dt plus c into e power minus pt. So where c is a arbitrary constant, so we can write the equation here. So in where x place lo what we have, x place lo here we have I, p, what is p, that r by l. So di by dx, what is x here, that x value is t. Okay, so di by dt here, so di by dt. And next, what is k value? K value is nothing but that is v by l. So v by l. So we can write the equation by substituting those values here. Then what we get? I equals to c into e power minus r by l into t plus e power minus r by l into t integration of v by l, that is k into e power pt, that is r by l into t dt. If we simplify this one, then we'll get I equals to c into e power minus r by l into t plus v by r. Here e power cancel, then here v by l, that v by r we can get. So whenever here, if time t equals to 0, thus at what happened, time t equals to 0, is there any current produces? No, that I value is equals to 0. So then you substitute this value in the equation 1. So substitute equation 1. Then what you get? 0 equals to c into e power, t value we are going to substitute 0. So e power 0 plus v by r, that c value, that c is equals to c into e power 0 value is 1, so minus v by r. So c value is equals to minus v by r. Okay, so now you substitute that value in the equation 1, that I is equals to v by r minus v by r exponential of minus r by l into t. So this is a final equation of your RL circuit, or else we can take it as common, v by r, then I is equals to take v by r as common, so 1 minus exponential of minus r by l into t. Okay, t. So this is your final equation. So here, whenever you substitute some I values, so I values, if you substitute I as 2t, so whatever I value as 2, t value as 2, then whatever the values that are that exponentially decreasing. So here let us take, what about VR? We can calculate the voltage across resistor. Voltage across resistor, that is VR. How can we write it? I into R. So what is I here? What you got? That V by R into 1 minus exponential of minus R by L into T into R. So R will cancel out. So that V into 1 minus exponential of minus R by L into T. This is a final equation, that is voltage across the resistor. So in a similar way, you calculate the voltage across the inductor. Voltage across the inductor. What is the voltage across the inductor? That VL is equals to L into di by dt. where L as usual L into d by dt of I value what you got 1 minus exponential of minus R by L into t V by R. So this is your I value. So if you simplify this one, what you got? That value as L into V by R, you take it as common, that write it outside. So here you write the derivation of 1, that is equals to 0. So derivation of exponential term, that is minus R by L into exponential of minus R by L into t. Okay, so here minus R by L, this term is minus, so total that value will become plus. So this is a derivation of exponential minus R by L into t. So final, if you write this one, that is L will cancel out, R will cancel out. So V into exponential of minus R by L into t. Okay, so which is exponentially decaying. So there in R, what you got? That value as exponentially 1 minus. So 1 minus means nothing but that is exponentially increasing. Here V into exponential. So we can draw it as if this is a response of RL circuit. Here we are going to draw the response for the inductor voltage as well as a resistor voltage. So let us take this V is the input voltage what you applied. According to the input, our V resistor, that is exponentially increasing. So this is V R. What about inductor? Inductor value initially that is high and finally that is reaches to 0 like this. So this is V L. And here x-axis we are going to take time t, and here on y-axis we are going to take output response, that is V0. This dotted line indicate that is input voltage. So by this, like this we are going to calculate the DC response of RL circuit. Just we taken one circuit that is RL or connected in series. For that one we are going to apply DC voltage. So DC, whenever you apply DC voltage, some voltage will be induced in that one. According to the current passes through that resistor or inductor, that will produce some voltage drop across the resistor as well as the inductor. So here whenever the switch is closed, that will act like a closed loop path. So here we written Kvl equation. So Kvl equation we written, that is in the form of which is dy by dx plus px is equals to k. So for this one we can write the complementary function as well as particular integral. So this is called as a particular integral and this is called as a complementary function. So we return those two, then we'll get I value. So that I value we got, and constant value is also we got, that we are going to take condition whenever the current is 0, that whenever the time there is no time, that is initial time, that current value will become 0. So that value, from that we are going to get the C value here. So C, by that your current value is I equals to V by R. So here we are going to calculate voltage across resistor and inductor by taking the formulas of V is equals to IR, VL equals to L into di by dt. We substituted I value there and we got the graph like this. So if you want to calculate the power, or if you want to know about the response of a power in that RL circuit. So power means power, that P equals to V into I. So whatever the power dissipated in the resistor, that V R into I. VR we already got it, V into 1 minus exponential of minus R by L into T. And here what is I value? I value is 1 minus exponential of minus R by L into T, that is V by R. So likewise you can calculate PL also. So PL, that is VL into I. So we know the VL value and I value. Substitute those values, we'll get V square by R into exponential of minus r by L into t minus exponential of minus 2r by L into t. So this is PL as well as PR. So if you draw the graph for these two, then that response will be like this. So which is here t as a x-axis, I am taking P naught, that is P on the y-axis. So P, nothing but V into I, or else you can take it as V square by R. So this is our V square by R value. So then P value, we are going to get same exponentially increasing. There is no change. So this is exponentially increasing. That is resistor R. But here we got V square by R, right? That is subtraction. So that response will be changed like this. That is, this is a response for the PL. So this is a way we can calculate the DC response of RL circuit. So next we'll go for the DC response of RC circuit. So DC response of RC circuit. So RC circuit means here we need to take R and C as a network. This is R and this is C. Here I connected, and from here I am going to apply voltage, that is V. V voltage applied here. This is R. So let us take one switch is here. So whenever the switch is closes, then that will acts like a closed loop system. So you apply the KVL here. So same process, just apply KVL here. V minus I into R current. What is the current equation in the, what is the voltage equation in the capacitor? That is 1 by C integration of I dt equals to 0. Okay, so here you V equals to what you can write? IR plus 1 by C integration of I dt. So here V, what is V here, Nana? Here can you apply differentiation here on both sides? So differentiate. That differentiate nothing but differentiation of constant, that value is equals to 0. Here R into, we are writing for I, so that is di by dt. So differentiate the current with respect to time t. Okay, so plus 1 by C integration of I dt and derivation, that both will be cancelled out. So 1 by C, that's it. So 1 by C plus R into di by dt will get. So if you write in the way like this, so di by dt should not have any constant. So di by dt plus 1 by RC equals to 0. So 1 by RC equals to 0. So if you write here 0, no, so can you calculate the equation by particular integral as well as complementary function? We will get I value as C into e power minus 1 by RC into t, minus that t by RC. So whenever at t is equals to 0, what happened? The current, that current I is equals to V by R. That capacitor will be acts like a open circuit. So here only resistor current, that is V by R, you can get. So you substitute these values, that t is equals to 0, that V by R is equals to C into e power, this value is 0, nothing but e power 0. Then C value equals to V by R. So you substitute this value in the equation 1. Equation 1. What you get? That I is equals to C into, so V by R into e power minus t by RC. So this is a current in the RC network. So if you calculate the voltage across the resistor, then voltage VR equals to R into I. You substitute that values R into I value, that is V by R into e power minus t by RC. So what you get? That V into e power minus t by RC, which is exponentially decaying. What about capacitor? Vc is equals to 1 by C integration of I dt. So 1 by c nothing but 1 by c integration of I dt, that is v by r into e power minus t by rc into dt. So you simplify this one, then you will get Vc as Vc equals to, which is V into e power minus t by rc plus c. So for the c, take initial conditions at time t is equals to 0, c is equals to v. Then the total Vc value is equals to V into, here you substitute V, then you take V as common. So that V value, that is V into 1 minus exponential of minus t by rc, minus t by rc. So 1 minus nothing but that is exponentially increasing. So which is opposite. In RL circuit, resistance voltage will be increasing. Here resistance voltage will be decreasing, capacitive voltage will be increasing. Nothing but capacitor will charge to the maximum voltage. So here this is V naught and here you take that is T. So 0 here. So that voltage VR which is exponentially decreasing. So VC that is exponentially increasing, VC. So this is VC and this is VR. The same way you can calculate the power also. Power which is exponentially, so power graph I will draw. So this is a power graph. And here which is exponentially decaying. So this is V square by R. So here I am taking P as output and here this is T. And so this is response of PC and this is response of PR. So this is about RC circuit. So we can, next we'll go for the DC response of RLC circuit. DC response of RLC circuit. Same pattern, just we are going to take 3 components as in series. So here I am taking resistor as well as inductor as well as capacitor here. So capacitor. So from here I am going to apply the voltage, that is V, and here I connected one switch. So this voltage is V, let us take RLC. Okay, so same you apply KVL here. So the current passes through the network is I, let us take. So I. So what happens? V minus IR minus L into di by dt minus 1 by C integration of I dt equals to 0. So if you apply differentiation both sides, or else before that one you write V is equals to IR plus L into di by dt plus 1 by C integration of I dt. So apply differentiation, then 0 is equals to R into di by dt. So here you are applying differentiation, right? So plus L into d square I by dt square plus 1 by C. So if you simplify this one, like constant L you can send that side. So then d square I by dt square plus R by L into di by dt plus 1 by LC into I equals to 0. So we can write like this as nothing but, if you take this derivation as d, then d square plus 1 by R by L into d plus 1 by LC equals to 0. Okay. So roots, can you calculate the roots? Yes. Calculate the roots, that d1 d2 equals to minus r by 2l plus or minus under root of b square minus 4ac by 2e, like in the format. So 2l whole square minus 1 by lc you got. So here you can get the different responses for this graph, for this equations, whenever you take the condition in the root, if root value is greater than or equals to or less than. So those 3 types of graphs you will get. So like this you are going to calculate the DC responses of RL, RC and RLC. Okay, so in the next class we'll see about which is AC responses, or also called as a transient responses of RL, RC and RLC circuits. Thank you.